Alright, so let's go through what we have to do for Z transform. I will assume that you have some basic knowledge of Z transform, and we will try to understand it in a slightly deeper and different level. The input to the Z transform is the discrete time sequence. And again, n is discrete. N is from minus infinity to positive infinity. The definition of the Z transform, so this arrow with the ZT on top says that we are now pushing x of n into a Z transform machine, and out comes x of z, and the operation on x of n looks like this. It is x of n, the input, multiplied with z to the power of minus n. And of course, now the question is, what is z? And z is the complex number. So here says I belong, z belongs to, then this funny symbol is the complex number shorthand notation. So z is nothing but a plus jb, any a plus jb, or any, normally you would write it as in polar form or complex exponential form, AJE phi, where here is the magnitude and here is the base. Here is the rectangle form. Here is the complex exponential form. Okay, later on you realize that we always prefer the complex exponential form because it is more elegant. It will make our equation more compact. Right, now if you look at this and now you compare to discrete time Fourier transform. How do we write discrete time Fourier transform? X of n goes through dt ft, gets me xej omega, and then this equation looks like n equals to negative infinity infinity x of n e minus j omega n. Yes? Right? That's the definition we have given you previously. And if you now compare this equation to this equation, the only difference is that z is equals to e j omega. So when z, the complex number, is replaced by 1 e j omega, then the Z transform and the DTFT looks the same. Okay? So what does Z equals to 1 e j omega means? So let us now try to understand what does this statement means. Means all of complex number Z that is equal to 1 e j omega. Okay, so now what does this mean? All of complex number z equals to 1 e j omega. 1 is already given to you, cannot change. So what can be changed? Only omega. And omega means all omega belongs to the real number. And now you will remember, what is 1 e j omega? 1 e j omega is a rotating phasor with amplitude 1, and this is omega making. So I'll now draw 1 e j omega for you. I'm now first drawing the real line, okay? And if this is the real line 0, sorry, this is the point 0, this is the point 1, this is the point minus 1. Now I will draw the imaginary line, and this is the point j, and this is the point minus j, and this is the imaginary line. And we are saying if this is a real line, normally we say the real of z, the imaginary part of z, and we say that z is the complex number. Okay? And now I'm going to draw the circle for you. This circle is called the unit circle because he has radius 1. Any value along this radius is 1. And this is omega, correct? So this point is 1 e j and then omega 0. Agree? And then you realize that as I let omega go from 0 to 2 pi, I make one circle around this unit circle. Okay? And in fact, if I say from 2 pi to 4 pi, I make the same circle again. So once I tell you to do from 0 to 2 pi, it's the same as anything else. That's enough. And now you realize that when z equals to the unit circle, the z transform is the same as dt ft. Okay? So in fact, if you now see this, so xz equals to x e j omega when z equals to e j omega. Exactly the same, right? Because if you look at the equation, they are actually identical. So this is the one interpretation. So this is the first slide. So this is what is usually taught to most students if they understand the discrete time Fourier transform. All right. Now, why do we bother to have another transform? The reason is that we know that in the DTFT, if the sequence is not absolutely summable, then we have a problem. So when we say x of n, and we have a sequence of numbers, and it goes on forever, maybe this is 8, this is 5, and then this is a number, and 10, and 12, and so on. And this is n equals to 0. And when we try to sum this sequence of number, maybe some of them are minus, some of them are plus, and then it is not absolutely summable, because why? It goes from left-hand side to right-hand side, and it goes to infinity. Then, if it is not absolutely summable, you realize that you plug in the sequence into here. What will happen? It is the value multiplied by a complex exponential. Since the value doesn't die, fast enough, the keyword is fast enough, then this sum doesn't give you a number. It goes to infinity. And when it goes to infinity, we say that the discrete time Fourier transform of the sequence does not exist. That's what it means in this statement. All right. What else do we do discrete Z transform for? Well, the other thing we know, the nice thing about the DTFT is this. DTFT allows us to do yej omega equals to x e j omega h e j omega. Allows us to do what? Multiply in the frequency domain to perform what, guys? Yes, to perform x of n, h of n, y of n equals to h of n convolved with x of n. And this operation is very expensive in the discrete time domain. I think it's close to like O(n) square operation, big O, operator O, n square, the length of the sequence of this length and this length. While here, we are multiplying only, and then it is very fast, of n sequence. All right, so DFT allows us to do that. You realize that we can perform Z transform, and we get x of z, we get h of z, and interestingly, the convolution becomes same multiplication in the Z domain. And this is point number 2. It says that, like the DFT, convolution in time becomes multiplication in frequency, and that is why we are also interested to do the Z transform. Right? What else? This is the interesting thing. Of course, we also like to play with difference equation, and in the difference equation, now I'm going to give you a concrete difference equation. Y of n equals to x of n plus x of n minus 1 plus 1/3 y of n minus 1. Now, what do we call this? The what? The difference equation describing the input and output relationship. So then the next question is the system an infinite impulse response or a finite impulse response? Yeah, there's a feedback. So typically, infinite impulse response. Of course, in the lab, I show you that not all feedback means infinite. Yeah? But in this case, it is definitely infinite. Now, Z transform has some very nice algebraic operation. If I say Z transform of x of n, then you can think of it as a notation change to x of z. Okay? Okay? And of course, Z transform of x of n minus 1, we get z minus 1, x of z. And now we have Z transform of alpha, okay? Y n minus 1. What do we get? Alpha, yeah? And then Z minus 1. Yes, because this is y. All right, with these three things, I have just only applied one single rule, or two rules. One is the scaling principle, the scaling property of the Z transform. And the second one is the property of the delay. Yeah, that's it. So there are two properties I apply. With these two properties, I can now convert my difference equation through my Z transform. All right, so y of n becomes, and now the rest I can do, plus 1/3 y z minus 1. Okay? And now we have it in the difference, we have just converted very quickly the difference equation to the Z transform, and now I bring it together. Y of z, 1 minus 1/3 z minus 1 and I have this equation, okay? And of course, I'm interested in something called a transfer function. What does a transfer function do? It shows me how my output is related to my input. It's called h of z. And I just told you, it relates my output to my input. So h of z equals to y of z over x of z. Yeah? It is the ratio between my output in the z domain to my input in the z domain. And equals to, so implying y of z is equals to x of z, h of z. Okay? Now, when we reach this step, I want to find h of z. You will realize that we want to find h of z because h of z is what in the time domain? What is h of z in the time domain? Impulse response. So you realize that inverse z transform gives you h of n, the impulse response. And that is why we are always finding the impulse response in all the domain. In the z domain, which is called transfer function, and in the Fourier domain, which is called frequency response. Right? So now we are here. Therefore, h of z is equals to, I substitute the equation, 1 plus z minus 1 over 1 minus 1/3 z minus 1. And now you realize that my equation is in the negative power of z, which I don't like, because usually you don't know how to do pole and zero plotting in the negative power. So what do you do? Yes, thank you. And we now reduce this to z plus 1 over z minus 1/3. And in this, it is now very obvious. When z equals to negative 1, what happened to h of z? H of z becomes 0. So we call the factor z equals to minus 1 a 0. Yeah? So the 0. When z equals to plus 1/3, what happened? Hz becomes, I substitute 1/3 here, what will happen? 1/3 minus 1/3? Yes, 1/3 minus 1/3 is 0, and 0 is at the denominator, and it will make my hz equals to infinity. We call z equals to 1/3 a pole. And now I can draw the pole zero diagram. Okay? How to draw the pole zero diagram? Again, we are drawing where z is. So first we draw the real part of z. We mark where the 0 is. We mark where the 1 is. We mark where the minus 1 is. And now I draw the imaginary part of the z. We draw where is the j. Where is the minus j? Now we draw a circle. And now I will draw where is z equals to minus 1. Where is z equals to minus 1? Here. Because he is a 0, I draw a 0. And at z equals to 1/3, here. 1/3. So this is the pole zero diagram. Can so far? Now, the next question typically is the system stable? So this system is a causal system. I must tell you it's a causal system. If I never tell you it's a causal system, you can also assume it's a causal system, because in our DSP world, we are typically dealing with the causal system. Okay? Now, if it is a causal system, you now draw a circle around the furthest pole. There's only one pole, so it's very easy to draw. This is at 1/3. What about this one? What's this point? If this is 1/3, what is this point? Minus 1/3. This is j 1/3, j minus 1/3. So this is a circle of radius 1/3. And because I told you it's a causal system, where is the ROC, guys? Outside the small circle I have just drawn. So this hairy thing is the ROC. I can also say the ROC is Z, absolute value of Z, what? Greater than 1/3. Okay? So anyway, I'll come and revisit the problem, you will see. Finally, does the ROC include what? Unit circle? And the answer in this picture is yes. And when it is yes, therefore, system is what? That's it. Right, some notations. h of z is called the transfer function. H of z, from h of z, you can find h of n, the impulse response of the LTI system. From h of z, you can verify the stability like what I have done. And finally, what about h e j omega? Yes, the frequency response. And now I have given you h of z. So I've given you h of z. So how to write h of e j omega? H of e j omega is equals to h of z by replacing what? 1 e j omega, right? And equals to, if I replace this by the equation, it's nothing but yes, that's all. And now I ask you, solve for omega equals to 0, pi 4, pi 2, pi. What am I asking you to do? I'm asking you to find the what? Frequency response. This is what? Frequency response. At this value, right? So now I will solve for omega equals to 0. H, E, J, omega equals to 0. What does that mean? It means 1 E, J, 0 plus 1. 1 E, J, 0 minus 1/3. Answer is 2 over 2/3. Answer is 3. Okay, that's it. All right. Did I make a mistake here? Let me check. Three. Okay, guys, see? I analyze it, and it's 3. What about analyzing at, what about H, E, J, omega equals to pi? This is 1 E, J, what? Pi, right? Plus 1. 1 E, J, pi minus 1/3. What is 1 E, J, pi? So it's minus 1 plus 1 divided by whatever number it is below. Answer is 0. Very good. And can you see it reaches 0? Can? So now any numbers in between, all you need to do is to substitute this. So it's wonderful, isn't it? Wonderful that, you know, what was very complicated to do the discrete time Fourier transform looks very simple now, yeah? By simply substituting z equals to e j omega.